Today we'll be presenting the third progress report of our project titled Cross-Lingual Prototypicality Bias in Visual Language Models. This work extends the proto-bias benchmark proposed earlier this year. The main question we are trying to answer is whether modern visual language models or VLMs make decisions based on the actual meaning of an image and text, or whether they rely on stereotypical or prototypical visual patterns that they've learned through internet datasets. In this report, we'll also investigate whether this behavior changes when the same prompt is written in different languages. So throughout this presentation, I'll first briefly recap our previous findings, then we'll introduce the new experiments that we performed for this report, discuss the results, and finally conclude with the implications and future work. So before discussing our experiments, let's first understand what prototypicality bias really is. So visual language models are increasingly being used for tasks such as image retrieval, image capturing, and evaluating generated images from like AI generated images. Because of this, they're often replacing or assisting humans when deciding whether an image matches a text prompt or not. Ideally, the model should focus on the semantic meaning of the prompt, but many models instead rely on some shortcuts. For example, suppose the prompt says an animal by a pond with exactly 2 bamboo stalks in the background. So one image may satisfy the prompt perfectly, but perhaps the animal shown is unusual or less common to be found. Another image might contain a panda which is strongly associated with bamboo, but the number of bamboo stalks may be incorrect. Humans generally choose the semantically correct image because they pay attention to details. And many automatic evaluation systems prefer the panda simply because it looks like the more typical example. This phenomenon is what is called prototypicality bias. So instead of understanding the prompt, the model is relying on visual stereotypes learned during training. The proto-bias benchmark was specifically created to measure this type of failure. Okay, now let's to study this problem. The proto-bias dataset contains carefully designed image pairs. So the image pairs left and right, 2 pairs, and then the first image is called semantically correct or SC image. This image satisfies every detail mentioned in the text prompt. The second image is called prototypical adversarial or PA image. It looks more typical or stereotypical, but actually violates some part of the prompt. On this slide, we see examples from 3 different domains: animals, demography, and objects. In every example, humans consistently select the correct image. Proto-score, which is specialized evaluation metric, also agrees with the human judgment. However, widely used models such as CLIP, PICScore, and VQA frequently select the prototypical but incorrect image. This clearly demonstrates that many automatic systems are influenced by visual stereotypes rather than semantic correctness. These carefully controlled image pairs form the foundation of all experiments that we will present today. So our extension is that the original proto-bias benchmark was designed only for English prompts. Our main contribution is extending the idea into a multilingual setting. Instead of changing the images, we keep the image pairs exactly the same. The only thing we change is the language of the text prompt. We translate each prompt into 7 different languages while keeping the visual content identical. This allows us to isolate the effect of language. If the model changes its decision or simply because the prompt is written in some other language, then the model is introducing language-specific expectations into its reasoning. Based on this idea, we formulated 2 research questions. First, is the bias consistent across different languages? And second, is the bias stronger in socially sensitive domains such as demographic attributes? Now, since everything except the language remains constant, this becomes a well-controlled experiment for studying cross-lingual bias. So, where this sits, bias structure and multilingual, this is a related work that we've discussed in reports 1 and 2. So, there are certain related work that we've done previously. Yeah. Now, the story so far. In reports 1 and 2, we initially believed there was almost no effect. The average error rate stayed close to 50%, which suggested that the bias was relatively weak and did not depend much on language. However, when we analyzed the data more carefully, we realized that this average was hiding some important patterns. Instead of looking only at the overall results, we divided the data according to different social attributes such as wealth, morality, power, and intellect. This revealed that the bias was actually more stronger for things like wealth and power, while morality and intellect stayed close to random choice. We then repeated these experiments using two completely different visual language models, Quinn and Intern VL. Although the models were developed independently, both showed almost exactly the same attribute pattern. We also observed that some languages, particularly Bengali and Greek, consistently produced higher levels of bias than English. So by the end of report 2, we already knew two important things. First, the bias depends strongly on type of attribute being evaluated. Second, there appears to be a genuine language effect. This naturally led to the main question addressed in report 3. Where exactly does this bias originate? Does it arise only when the model generates its final answer, or is it already present much deeper inside the shared image text representation? Okay. Now, the feedback we got from report 2, that's us acting on those feedback. Before presenting the new findings, I'd first like to explain how we address those report 2 feedbacks. Our mentor suggested three main improvements. The first suggestion was to investigate whether the same patterns also exist in the animal and object categories instead of focusing only on the demographic data. To address this, we broke both categories into finer subcategories and analyzed them separately. The second suggestion was to include additional text to image evaluation metrics, specifically CLIP score, PIC score, and VQA score. These metrics allows us to measure image text alignment without directly asking a visual language model to make a decision. We implemented all these three metrics and evaluated them using the translated prompts. Finally, we were asked to include more visual examples and make presentation easier to follow. So we added example image pairs and interactive visualizations, which you will be able to see in the upcoming slides too. Okay, next is about the animal and object results. This is again us acting on those received feedback. The first new experiment was to examine whether the animal and object categories also contain hidden structure. Previously, the average error rates were close to 50%, so they appear almost random. However, averages can sometimes hide important differences. When we divided these categories into smaller subcategories, a much clearer pattern emerged. For animals, birds and generic animal classes showed relatively high bias, whereas mammals were much closer to chance. Similarly, for objects, vehicles showed noticeably stronger bias than furniture. If we look at the graph, we can see that the error rates vary considerably across these subcategories. More importantly, the same ordering appears in both Quen and intern VL. This tells us that the effect is not random and is not specific to a single model. Instead, the bias depends on what kind of concept the model is trying to recognize. So, even though the overall average suggested no bias, a more detailed analysis reveals consistent structure across different domains. Now, the attribute access. This slide summarizes one of our strongest findings. Here we analyze demographic data according to different social attributes. At first glance, the overall error rate is around 0.58, but this average hides a very large variation. If we examine each attribute separately, we see that wealth and power produce much higher error rates than morality or intellect. In other words, the models are much more likely to rely on visual stereotypes when judging concepts related to wealth or social status. A likely explanation is the data used during the training. Large internet datasets contain many stereotypical images of rich or powerful people. As a result, the models learn strong visual prototypes for these concepts. In contrast, there is no universally accepted visual appearance for someone who is intelligent or moral. Because no stable prototype exists, the models cannot rely on these shortcuts. This explains why the bias is much weaker for morality and intellect. So, the key message from this slide is that the type of attribute strongly influences the amount of prototypicality bias present. Now, the replication across models, a natural question is whether these findings are specific to one model family. To answer that, we repeated the experiments using both Quen and intern VL. If we look at the slide, what it presents, we can see that both the models produce almost identical patterns. The odds ratio for wealth compared with morality are approximately 3.7 for Quen and 3.1 for intern VL. Both models also produce extremely small p-values, around 2 times 10 to the power of minus 14. Such small p-value indicates that these differences are statistically very significant and are extremely unlikely to occur by chance. The important takeaway is that this behavior shown is not a bug or limitation of one particular architecture. Instead, two independently developed visual language model families show the same attribute dependent bias. This gives us much greater confidence that the phenomenon is genuine and broadly acceptable and applicable.
Yeah, so thanks, Rishav. So far, we have seen the bias is attribute specific and shows up in both models. Now, I want to ask a deeper question. So, where does this bias actually live? Is it just how the model answers, or it is baked in deeper? So, to test this, we dropped the VLM entirely and used three text-to-image matrices, which are clip score, pic score, and VQA score, that just measure how well the image matches the text. And we can have a look. Like the clip score and the pic score falls for the typical but wrong image on about 70% of items. And at the same time, VQA score, which is the green one in the graph, and also the strongest one, is more robust. It's near chance overall. But all the three keep the exact same shape, so the bias peaks on whales and fades out towards morality and intellect. So the shortcut isn't something the model invents when they are answering. It is actually already sitting in the image text representation. And here is the link that ties it together. So for each image pair, we asked, does the VLM pick the same image? The matrix score are higher. So when the matrix before the correct image, the VLM picks correct about 65 to 70% of the time. But when the matrix leans towards the typical image, the VLM only get it right at about 35 to 40%. So that is a gap of roughly 0.3, and it holds across both model and all the three metrics. So we can see the behavioral bias and the representational bias are not two separate things. They're actually the same phenomenon showing up but at two different levels. So now we can ask the initial language question, which is our original motivation. So with the initial four languages, the bias looked totally flat across languages. But once we added Bengali and Greek, so they are lower resource and different scripts, and after that a real effect shows up. So the prompt in Bengali and Greek triggers significantly more bias than English, and also this is in two models. So importantly, the attributes pattern stays the same in every language. It's the overall level that shifts up. So language doesn't change what the model is biased about. It actually changes how strongly it's biased. But then we did something that the mentor suggested, like we ran the matrix on the translated prompts too. So using a multilingual clip, and this gave us a really clean split. So the representation is biased in every single language. So we can see it's all above the chance. But it's flat across languages. No Bengali or Greek spike at all. So if there's anything worth noticing, it's only the Bengali slightly lower. So put these two slides together, the attributes bias live in the representation, and the language effect seems that it comes from how the VLM itself handle those less familiar languages, like the low resource languages, but it's not from the image text alignment. Now the obvious pushback, maybe Bengali and Greek just get worse translation, and that is the whole effect. So in order to reply this, we back translated every prompt and measured the drift. And it's actually the opposite of what you would expect. The most biased languages, which are Greek and Bengali, have the highest translation fidelity. So the least biased one, Hindi and Russian, drift the most. If bad translation were driving the bias, that relationship would go the other way. So we can prove that it is not the translation artifact. And we also need to notice another potential confound, because every adversarial image also have like tweaks one visual knob: count, color, scale, layout, spatial. Maybe the model isn't just reacting to prototypes at all, it's just reacting the change of color. But if this color artifact, color would spike, and instead color is the lowest. So we can see the bias is actually highest when the Q is hard to perceive, like count or scale. And critically whales, it still beats morality within every single knob. So the attributes effect isn't a knob artifact either. And we did one more check. So do the two models fail on the same image pair or different ones? We correlated their per item error rates, and it is actually 0.68. So the trap is largely item intrinsic. It's an objective property of the image pair itself, not just one model's quirk. It's not a perfect one, though about half. It's still model specific, strongest agreement on demography and weakest on objects. So let me pull it all together. The bias is a shortcut with three parts. So first of all, a source, the attributes. So a visual prototype exists for whales and stages, but not for morality and intellect. And that map is largely item intrinsic. And the second one is the trigger. So the trigger is signal weakness. The model falls back on the prototypical when the real cue is hard to perceive, or when the prompt language is unfamiliar. And third, it's a home. So it is actually the representation. All three metrics carry the same signature, and the VLM's choice tracks them. So the attributes decide whether a shortcut exists, and the signal weakness decide how much is taken, and the shared representation is where it lives. But also we need to notice a few honest limitations. This is only a one seed and one translation backend, so adversarial knob covaries with the prototype. So it's not a fully clean manipulation. Our demography cells are small, so the whales is only about 31 items per language. So we lean on confidence intervals. And the T2L metrics were mainly the English prompt, though we were started extending them, and we had to drop a Quinn 32B because it was too slow on the hardware we had. And where we are going. First, extending VQA score to the translated prompts, the way we did for CLIP. Second, it's about the scale axis. So Quinn 32B maybe in 4-bit, does the bias shrink as models get bigger? And the third one is more model families to see how general the language effect is. And finally, we want to pin down the language effect itself. So we want to see how much is the source and how much the script and how much is cultural loading behind that Arabic, Bengali, Greek spike. And that's it. We built the first multilingual, multi-model proto-bias pipeline across 7 languages and 2 model families, and trace the bias all the way down to the shared image text representation. So thanks for listening, and we're happy to take any questions.